Happy Sunday to you. That's what day it is that I'm making this video, and we're going to be starting on Chapter 4, Lesson 4, Rational Numbers. The pacing guide says this is going to be a 90-minute long lesson, 2 days in class, we shall see. And the content objective says students will reason about rational numbers using a number line. Sounds pretty simple. Let's get started. Of course, you want to highlight your chapter, your lesson title, Rational Numbers. And it says that elevation below sea level are represented by negative numbers. Sometimes those elevations are not a whole number measurements, but expressed as fractions or decimals. The table shows the lowest elevations on Earth for each continent. And you can see they got a bunch of continents listed here. And some of them, wow, Dead Sea in Asia, that's really low, but not even close to the subglacial trench in Antarctica. That's really low. For our talk about it, do you think that the process of comparing and ordering the elevations will be different than comparing and ordering the set of integers? Explain how you think the process may be or may not be different. These are the things we're going to learn about in this lesson. Recall that natural numbers are numbers from the set 1, 2, 3, 4, and so on, and it continues without n. Natural numbers are numbers that occur in nature. Basically, can you hold it and it still be alive? You can hold 1 sheep, you can hold 2 sheep, you can hold 3 sheep. You can't hold 0 sheep. 0 sheep does not exist. And having half a sheep, well, you get pork chops, I guess, but that's about as good as it's going to get on that one. The set of whole numbers are all of the natural numbers and 0. The only difference between whole numbers and natural numbers is the existence of 0. That's it. Integers are going to be whole numbers and their opposites, which means all the natural numbers, all the whole numbers, which is 0, and the opposite of the natural numbers, -3, -2, -1, are opposites of 1, 2, and 3. Therefore, this entire set encompasses your integers. And finally, oops, I didn't highlight a letter there. Let's try that again. Any number that can be written as a fraction, a divided by b, where a and b are integers and b is not equal to 0, meaning your denominator is not 0, don't stress that, we will learn that later in life, is called a rational number. A rational number can always be represented as a point on the number line. Here's the skinny. If it can be written as a fraction, it's a rational number. If it can be written as a terminating or repeating decimal, it's a rational number. So what's an irrational number? An irrational number would be something like pi, a non-terminating, non-repeating decimal that goes on and on forever. So on your Venn diagram, you can see natural numbers, then whole numbers, and then integers. Integers are both whole numbers and natural numbers and their own thing. Whole numbers include all the natural numbers, and natural numbers, well, they're just natural numbers. So if we were to click on something here, you get some representation of rational numbers. So your natural numbers, 4, 10, and 9, the whole number adds zeros, and your integers adds the negatives to it. If we were to take and, what are we changing here? I have no idea why they're doing that. Oh, and then out here, you've also got other rational numbers, such as the fractions that you see going on here. So those are other rational numbers. Integers are only going to be these. See, they took away your fractions and your decimals, so integers cannot be a fraction or a decimal answer. Your whole numbers are only going to be these, and your natural numbers, those are the things that occur in nature, like the nice cuddly sheep, before it becomes a pork chop. Not a pork chop, a lamb chop. Forgive me, I got confused there. So, is -3.77 or 3 77/100 a rational number? Well, let me ask you this. Is it a terminating decimal? Yes, it is. If it's a terminating decimal, it's going to be rational. It does not matter that it has a negative sign in front of it. So let's take a look how we would graph rational numbers on a number line. Rational numbers and sets of rational numbers can be graphed on a horizontal or vertical number line. A set of rational numbers is written using the braces that you see here and here. That's what we call that funky looking parenthesis. We call them braces, kind of like the things that go on some of your teeth. To graph a rational number on a number line, place a dot on its location. So we're going to take and highlight this part of it because that's the important explanation of the problem, and then we're going to take and graph the rational numbers. So let's see if we've got to graph positive 2.5, negative 1 3/4, and 0. So positive 2.5, that's going to be right there at 2.5. Next, they took and added the negative 1 3/4. You had negative 1, negative 1 1/2, and then halfway between 1/2 and 2 was going to be a negative 3/4. And finally, the last one we're going to have is 0, and of course 0 is the easy one. It lands on 0 on the number line. Easy math. Suppose the same numbers are graphed on a vertical number line. Compare and contrast the locations, yada yada. Well, let's see. You can see on a vertical number line, now the negative numbers are going down, your positive numbers are going up, but other than that, everything else is the same. They all get graphed in the same exact spot. They just took the number line and went doop like that, and everything's good. So let's take a look at another example. It says graph the set of rational numbers, negative 1/5, negative 7/10, positive 2 3/5, and a negative 1 8/10 on a number line. So let's do it. Moving forward, find the integer boundaries on the set. Your boundaries, your biggest number is going to be 2 3/5, and your smallest number is going to be negative 1.8. So your integer boundaries are going to have to be bigger than negative 2 3/5, and it's going to have to be smaller than negative 1.8. So I'm going to say I need to have a biggest number of 3 and a littlest number of negative 2 for our number line. Check that, and it said I'm right, but it also said I'm wrong. So I'm really confused because it says I'm right and it says I'm wrong. It's confused. I'm right. Next, we're going to use those numbers to build our number line. So you got our number line coming up here. Remember these squiggly things, they're called what? They're called braces. And on the number line, see, just like I said, it went to negative 2 on the left and positive 3 on the right. And all we have to do is select a point on the graph, yada yada. So let's go ahead and start doing that. We're going to start with our negative 1/5. Negative 1/5 is also the same as saying negative 0.2, also known as negative 2/10. So we're going to come down here. We got 0, we've got 1. These are broken down into tenths, so it's going to go boop right there at negative 2/10. Negative 7/10. Well, that one we're going to change a color to. It's going to be at right there. And the next one is going to be positive 2 3/5. Well, 3/5 is the same thing as 6/10. So we're going to take it and we're going to go 2 and 1, 2, 3, 4, 5, 6. So we have 6/10. And the reason we know they're tenths, if you count them out in between here, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 sections between each set of data values. And then our last one is going to be a negative 1 8/10. So let's get one more nice warm color. Negative 1 and 1, 2, 3, 4, 5, 6, 7, 8. It's going to go right there. Can we check it? Check our answers, and our answers are correct. Easy math. All right, folks, now it's going to be your turn whenever it comes up. There's your information that you have to graph. There's your number line. So on your devices, take and graph that information on the number line. You can use different colors or you can use all the same color. It makes no difference to me. All right, once again, our number line is broken down into into tenths. So you have 10 sections between each one. So negative 1/2, that's the same thing as saying negative 0.5, also known as negative 5/10. So that first dot is going to go right there. The next number we have is negative 1.5, or negative 1 5/10. So that one's going to go 1, 2, 3, 4, 5 right there. The next number we have is a negative 0.1, also known as negative 1/10. And that's going to be at 0, negative 1/10 right there. And our last one is negative 2 1/5, also known as negative 2 2/10, also known as negative 2 200. So that one is going to go, let's get a new color here, negative 1, negative 2, negative 2 1/10, negative 2 2/10 right there. And check our answer. Everything checks. Easy math. So what happens if we throw rational numbers, absolute values into the mix with rational numbers? Well, absolute value is just going to be the positive version of that number, so it's not really going to change things that much. The rational numbers 2.5 and negative 2.5 are both 2.5 units from 0. Even though they're on opposite sides of 0, the numbers that are the same distance from 0 on a number line and have the same value are known as absolute values. So, looking at this in words, use our flip card. The absolute value of a rational number is the distance between the rational number and 0 on a number line. Looking at it with a model, you can see that negative 2.5 and positive 2.5 are both 2.5 units from 0 on the number line. And looking at it in symbols, the absolute value of 2.5 equals 2.5. The absolute value of negative 2.5 still equals 2.5. All we're doing right now, guys, is applying what we already learned about absolute values to our rational numbers in decimal form. This is a pretty good talk about it here. It says, why is the absolute value of a number not the same as the opposite? Well, the opposite of 2 is what? Negative 2. And can negative 2 ever be a positive number? So then the absolute value of an answer is always going to be the positive version of that number. So nope, definitely not going to work. Now they want us to find the absolute value of rational numbers. The lowest point in a certain cave has an elevation of negative 53.4 meters. If the cave entrance has an elevation of 0 meters, evaluate the absolute value of negative 53.4 to determine the number of meters the hiker would descend to reach the lowest point. Well, the absolute value of negative 53.4 is going to be what? 53.4. So that's kind of pretty easy there. I think that answers all the questions for us. Yep, we can highlight that too. So let me highlight that as well. So select a point on the number line. So here's our number line, and we've got to go to negative 53.4, which is going to be, let's go down to, we've got negative 50, 51, 52, 53. Yeah, it's going to be just about right there. So halfway between 53 and 54 is basic. Check our answer, and it doesn't actually check the answer on this one. Oh well. So the next question, how many meters is 0 from negative 53.4? It is 53.4 meters from it. So we got an absolute value of the number is going to be a positive 53.4, and the hiker would have descended 53.4 meters. Easy math. Anybody can do this stuff. And now it's going to be your turn to pause the video and find the absolute value of the rational numbers. Check your answers, see if you're on track with knowing what you're supposed to do. And there is your problem. Work it. Did you get the right answer? Should have. The absolute value of 4/5 is going to be what? It's going to be a positive 4/5. That's all there is to it. The absolute value is the positive version of any number. Easy math. We're going to stop here for part 1. Come back and watch part 2 of rational numbers so you can keep learning all the exciting stuff you need for your homework tonight.